going to look at some of the mathematics behind it and develop a couple of formulas for it. Um, as we look at this over here, because our velocity is equal to frequency times wavelength, our frequency is equal to velocity over wavelength. As you can see in this case over here, in this case here, if this distance here was L, then what would the wavelength of this wave be? What would the wavelength equal? It would equal 2L, wouldn't it? Because this is half a wavelength here. So your frequency in this case over here, if this was situation 1, your frequency for 1 would be the velocity divided by 2L. In this case over here, though, you've got your frequency. So for this situation here, your frequency is equal to velocity over wavelength. What is your, if this again is L here, what is your wavelength? L. So it's equal to V over L. Now the velocity remains the same because the velocity is actually dependent on the, in this case, on the string, on the tension of the string and the properties of the string. So the velocity remains constant, but obviously you can see here that your frequency is actually increasing. This frequency will be double that frequency. So you'll find that with the wavelength changes and the frequency changes, the velocity stays the same. We'll develop some formulas for that. Okay, so we're actually going to look at 3 different situations. We're going to look at when you have where it's fixed at both ends, fixed at one end, and not fixed at either end, and then we'll compare it to music instruments. Those of us that are musicians here, any musicians around here? Who of us plays instrument? 1, 2, yeah, not. I thought there would be more here. All right, good. So there's actually I've got on the web page a very interesting. I've got a very interesting video that I found that looks at the clarinet and the what is it? There's another instrument, and it compares them, looks at them, so we can have a look at that. But here you got, this is the sort of demonstration that we got over here. This is your sort of standing wave, as we demonstrated a little bit earlier. Okay, so we're going to look at this idea of a fixed at both ends. When it's fixed at both ends, we're going to look at that. Now, in this case over here, this is fixed at both ends. We start with the simplest case, where we've got 2 nodes, one antinode. This is called the fundamental, or the first harmonic. All right, the fundamental note. Here we have got a wavelength. If this again, as we mentioned before, is equal to L, we have a wavelength of 2L, and we have a frequency which is equal to my velocity divided by wavelength, my velocity over 2L. Okay, that would be the case for that. So going to my next situation where I just have the maths of that. That's what we've just done here. That's called, notice here, this is called the fundamental frequency or the first harmonic. You've heard of that for those that are musicians. You've heard of that. This basically gives the first harmonic gives the actual note, the basic note, and then you get other harmonics that build upon that basic note. Now, if I go to my next situation, I now have, within the same thing, I now have a standing wave that's formed where we've got one full wavelength. So my lambda is equal to L. So we have lambda is equal to L. My frequency is V over L. Okay, I used a small L before. All right, so before for my first was over 2L, now it's over L. And this is known as my second harmonic. Okay, straightforward. Going down to going down to this situation, we have now got here. Now, this would obviously be my wavelength from there to there. All right. So I've actually got 1.5 wavelengths. L is equal to 3 over 2 wavelengths. My wavelength would therefore equal L divided by 3 over 2. So it would equal 2 over 3L would be my wavelength. Okay? And therefore my frequency would equal my velocity divided by my wavelength, so divided by 2 over 3L, so it would be 3V over 2L. Okay, you okay with that? All right, that's pretty straightforward. When you divide, you invert the fraction and you times. So this is your third harmonic. Okay, so let's just write it here and see if you can see the pattern. So you get your first harmonic, that was V over 2L. Your second harmonic was V over L, and your third harmonic was 3V over 2L. Okay, so can you give me for your nth harmonic, your formula for your nth harmonic? What would that be? NV over 2L is correct. Okay. So when your first harmonic, it's V over 2L. Your second harmonic, you've got 2 there, those cancel out, and you've got your second harmonic, third, 3 over 2, V over 2L. So you've got this over here is basically your harmonic series that you can form. You can form your whole harmonic series from this. We also have our wavelength. We can look at our wavelength. Our first wavelength was equal to 2L. Our second wavelength was equal to L. Our third wavelength was equal to 2/3 of L. Our nth wavelength would be what? Two over NL. Okay. Alright, so let's just check it out. When it's 1, it equals 2. When it's 2, it cancels out. When it's 3, it's 2 divided by 3L. Okay, so there is our harmonic series dealing with both the frequency and the wavelength. Okay, now none of these formulas actually are given to you in your data booklet, but you do need to be able to work them out. So it's that you do need to go to the basics for it. So that's a situation where you are dealing with where you've got a fixed point on both sides. Okay,